All right, ladies and gentlemen, I'm extremely excited for our next talk on graphs and excited to welcome Ralph Liu. Ralph is currently a software engineer at Nvidia, where he is working in the RAPIDS ecosystem on GPU-accelerated graph libraries like cuGraph and nx-cugraph. We're going to get to hear about all the cutting-edge work being done around solving law of graph problems at scale. Please join me in welcoming Ralph to the stage.
Good morning, everyone. Thank you all for being here. My name is Ralph Liu, and like she said, I'm a software engineer at NVIDIA working on the RAPIDS cuGraph project. And today I'm excited to present to you today of how you can use NetworkX combined with GPU acceleration. So I just want to start off by saying that this talk welcomes audience members of all levels of experience, whether you're new to graphs and NetworkX or you've been doing data science for a long time now. So a quick outline of what I'm going to talk about today is a quick intro to graphs and why they're useful, why so many people choose to use NetworkX for their graph workflows, what is dispatching and why is it the future of NetworkX, and then I'll be going over an example of using NetworkX to do graph analytics and community detection in a large graph. And finally, I'll recap with a tale of how we work with members like yourselves of the data science community to make NetworkX and nx-cugraph even better. So the goal of this talk is to give people like yourselves tools, people like students, researchers, engineers, data scientists, and such, to have the tools to go out and solve problems using graph. And we at RAPIDS want to make it as seamless as possible to scale up to large data sets as needed. And what we're doing here at RAPIDS is essentially trying to lower the barrier of entry for accelerated computing so that anyone, let's say with a laptop and any kind of GPU that's supported, can go out and explore cool data science use cases. So, quick intro. To start off, what are graphs and why are they useful? Graphs, if you haven't heard, are a way of representing data using things called nodes and edges. This is really basic, so if you've seen graphs before, please bear with me. Nodes are the individual entities in your data. These can be people, cities, bank accounts, and edges are things used to connect these entities together. They represent the relationships between the nodes. So think two friends are connected by a friendship, or roads connect cities and locations together, or you can even note two transactions between financial institutions as an edge occurring between the two nodes. And the simplest philosophy of why we should care about graphs at all is everything is connected. Everything in this world has some relation to one another. So a lot of the times when you're working with any kind of data, it's likely that the connections between the data points are just as important, if not more insightful, as the individual data points themselves. So the friendship between two people can actually reveal more insights about the two people within a greater community, and so forth. And graphs are really useful because they capture all of these things. So this is an example I really like. This planet graph is a great example of how to use a graph to represent some data. It visually displays it in a way where anyone can kind of understand what's going on. Here our sun, the planets, and their moons are the nodes, and edges are the orbit relationships. So you can see the Earth orbits the sun, that's one relationship, the moon orbits the Earth. And with graph also comes with something called graph theory or graph analytics. Basically, we have graphs now. What do we do with them? Well, graph analytics is the study of analyzing these interconnected data and discovering cool insights from the graphs to answer our questions or solve a problem. So by studying these relationships, we can discover insights like who is the most influential person in a friend group, or how do I find clusters or cliques in a larger graph? What's the quickest path to get from point A to point B in a city? And so many more applications. So virtually, I want to emphasize that all fields not limited to computer science can apply graph analytics and graphs to their problems. So what I mentioned earlier is NetworkX. NetworkX is a Python library for working with graphs. Why NetworkX? If you haven't heard, it's basically at this point the de facto standard for working with graphs in any programming languages, but particularly Python, because it is just really great thanks to all of its features. It's really easy to pick up and use. It's very intuitive, has a very Pythonic API, so it's very easy to get started once you pip install NetworkX, and anyone can work with graphs. It comes with a huge catalog of algorithms out of the box, so algorithms useful for solving specific problems that you might have, things like shortest paths, centrality, clustering, PageRank, I don't know if you've heard of these, and so much more. Also, data scientists love integration, and NetworkX integrates pretty seamlessly with tools that you guys like to use, such as Pandas, NumPy, Matplot for visualization, and so forth. Another great thing about NetworkX is that it's been backed by a strong open source community, which means it's been thoroughly vetted and bug tested over its 20-year lifespan now. And as it shows, just last month it had over 80 million downloads, and it has currently more than 15,000 stars on GitHub. So in summary, NetworkX is great thanks to its robust community, documentation. There's tons of examples and notebooks and tutorials. And if you ever have questions, you can ask the community, and they're always engaging in new discussions surrounding NetworkX. So it's great for researching, teaching, exploring data, and prototyping, sometimes production, but there is one downside to it being a pure Python implementation, which is that, as you see, it's very, very slow at scale. So in this figure, working with NetworkX and running an algorithm called betweenness centrality, I'll get to that more later. As the graph size scales up from thousands of nodes and edges to hundreds of thousands and millions, you can find yourself having to wait an unreasonably long amount of time to get the results that you want, which is not ideal. So a lot of the times, NetworkX users always say, we want NetworkX to be faster. And there are other graph libraries, but actually in order to make things fast without having to ditch all of the great things that come with NetworkX out of the box, my colleagues at Nvidia and the great team over at NetworkX came up with a brilliant solution together, and that's called dispatching. So before I actually explain what dispatching is, I'd like to just show it to you in an example. So I'm going to introduce nx-cugraph. This is a NetworkX backend created by us at Nvidia RAPIDS, and it essentially allows us to use GPU hardware to speed up existing NetworkX code. There are other NetworkX backends that each specialize in doing something better maybe than the default implementation. So here I wrote an example, it's really simple, called run betweenness. It essentially creates a NetworkX graph from a pandas data frame. The data is roughly 3.7 million nodes and a little over 16 million edges. It's information about US patents. And then I run betweenness centrality on it. Betweenness centrality is an algorithm in a nutshell that just tells us which nodes act as like the bridges that connect shortest paths from other nodes. It's more complicated than that, but that's the gist of the algorithm. And when I run it using NetworkX on a graph of this size, it took just less than 3 hours to complete. Now that's a lot of waiting. So instead, on a system with a GPU and nx-cugraph installed, I can reuse all of the same code. Nothing has to change. But all I had to do was enable dispatching in an environment variable. And you can see it now completed in just over 23 seconds. So that's dispatching in action. And dispatching is a mechanism, but it's also a philosophy where we get the best of both worlds. It's like designing an API that fits all use cases. So previously, to get faster on larger graphs, I mentioned users had to look to switching to other libraries. That also means there's always a learning curve. You have to change all of your code. You have to change all of your data pipelines. And this is a lot of overhead for a user who just wants to do the same thing on bigger data. So instead, with dispatching, we can help users solve that problem where they don't have to rewrite any of their code. and we can have NetworkX just serve as a singular user-facing API, and then dispatch algorithm calls to different backends as needed. So the huge benefit of this, it's pretty obvious, is that we can stay within the NetworkX ecosystem, taking advantage of its great docs, examples, and tests, while also allowing open source maintainers like myself to focus on actually implementing the algorithms without having to design a new library or rewrite all the docs that NetworkX already does better than everyone. So as a NetworkX user, it's great because you get more performance, no code change. And as a developer, you get to focus on implementing the things that go fast, and you don't have to pay the open source tax, is what we call it. So let's see what else we can do with NetworkX that makes use of dispatching in an example that uses real world data where I explored a large graph. So first, I'm going to introduce the data set that I use. It's a social network data set, social network websites. It's called Pokets. I apologize if I'm pronouncing that incorrectly. It's a social network in Slovakia. You can sort of think of it like their Facebook. I think it was the most popular site up until a couple of years ago, and then it got eclipsed by Facebook, sadly. The site has connected millions of users over its 15-year lifespan, and I found a data set containing information about the site from the Stanford Snap repository. It contains roughly 1.6 million users and information about 30 million friendships. So here's a quick look at the data. On my left, I have a data frame that contains information about the 1.6 million users. So each of these rows is a profile, and users filled out information on their profile, such as their age, their gender, the region that they're from, and things like hobbies, interests, although those were optional, so they're not always filled out. And on the right, we have information about the relationships. So it's a data frame that contains two columns. The source and destination are each people. And this is known as an edge list, where each row represents a connection between the two people in the columns. And it's fully anonymized, so it's trackable by the user ID in the relationships database corresponds to the user ID in a row from the profiles database. So I'll be using this graph to run something called community detection algorithms and see just how much dispatching can speed up exploring the data. So really briefly, community detection is a category of graph algorithms that helps us identify clusters of nodes that are more close-knit to each other compared to other nodes. And these, like the name mentions, can be thought of as small communities found within a large graph. And with a graph of this size, it might not be obvious upon first glance what this community is, especially when the nodes are not positioned neatly and you can't visualize it, right? So in a sea of 1.6 million users, I want to see if we can find some communities of closely linked people. And the community detection algorithm I chose to showcase today is called Louvain. The way Louvain works, I won't go too in detail with it, but it partitions the nodes in a way where it optimizes for something called modularity. So it partitions nodes into different communities, sees how good the modularity score is. If it's good, it will keep it. If it's not, it'll keep trying to partition them into better, more close-knit communities. If you'd like to understand Louvain more in depth, I recommend checking out the NetworkX documentation, as it goes way more in depth into how it works and the math behind calculating the modularity score. So here is what I cooked up. It's a small end-to-end example of running Louvain using NetworkX. So like earlier, I create two data frames, the profiles data frame and the relationships data frame. I print some information about their sizes, so you can see the 1.6 million users across 59 columns in the profiles, and 30 million friendships, aka edges, across the source and destination columns. And then after creating the data frames, all I have to do is create a graph in NetworkX by using from pandas edge list, and I print some information about the graph, so you see it has confirmed 1.6 million users and 30 million edges. Then I go ahead and call Louvain on the graph, and you can see that end-to-end, this entire workflow took about 39 minutes to complete. Once it completes, I just print some information about the communities that Louvain found. But upon timing this over and over again, I found that creating a graph takes roughly 1 minute and 45 seconds on average, and actually running Louvain in pure Python default NetworkX takes a little more than half an hour, which is really long. Now let's see what the same example looks like, but with dispatching to nx-cugraph. So all the code stays the same. Okay, it's not being cut off, that's good. And end-to-end, it now completed in just under 3 minutes, with the graph creation taking just around 5 seconds, and running the actual community detection algorithm took around 20 seconds. So that's over 90 times faster on the algorithm itself, and around a 9 times speed up for an end-to-end workflow. So instead of waiting around using dispatching and nx-cugraph, I kept my same NetworkX code and ran everything much quicker and had my results just like that. So with the results, I just played around with the data and examined some of the communities that we found. This is some of what I did. So you can see here, I'm looking for, from the results, I look for communities between a certain size. So I chose 50 and 200. And from the results of Louvain, I found around 8 communities that fit that criteria. So I went digging around and poking around those communities from the results. And I found one that really interested me, which was at index 29. I'll call them community A. So this community has a size of roughly, or exactly, 146 members. But the male to female gender ratio was way off, which interested me, and it has an average age of 21.6. So with the results, going back to the profiles data frame, I was able to see that there's roughly a 1 to 14 gender imbalance, male to female ratio, which is pretty odd for this community. And also over half the members are between the ages of 20 and 26. Moreover, this was really cool. When looking at the profiles for community A and looking at what they put in for their region, the result was a community that reported more than 2/3 of its members being from a western region of Slovakia called Sala. And this is really interesting because if you look earlier, we're only giving Louvain the graph, which is constructed from the edge list, which has only 2 columns, person A and person B. So Louvain didn't actually know anything about the user's profiles, and yet it was able to find a pretty non-homogeneous group of people who are all from the same region, very female dominant, and also happen to be very closely in age. They're all in like their early to mid 20s. So by using community detection, I was able to zoom in on this one small community within a greater graph of over 1 million people and gain insights about why they might be closely linked and why they're a close community. So I'd like to highlight that this is just one of many useful ways of using graphs and graph analytics, and there are a ton of other algorithms that you can use to solve other cool real-world problems. And since I was running with the GPU backend, it took far less time to actually get my results. So in the time it took for me to actually get my results from NetworkX, I was already able to explore the results and find cool insights like this with dispatching to GPUs. Now that I've shown you how community detection can be useful, I also want to tell you another story. This is an algorithm that has to do with community detection, but it's not about community detection again. So the algorithm here is called Leiden. So generally, it's an improvement upon Louvain, and it results in better connected communities and even runs faster. But I actually want to tell you that for a long time, Leiden didn't even exist in NetworkX. It wasn't supported. And there were some proposed implementations floating around, but nothing was concrete or officially added to NetworkX. And so a lot of people in the graph community wanted to see Leiden added to NetworkX. They didn't want to have to switch the whole library and pipelines and code, everything like that, just to call one algorithm when they could stay within the ecosystem. So the Rapids team noticed this and decided to meet this demand. and they added Leiden to NetworkX as something called a backend-only algorithm. So what this means is that now users can call a fully functioning and very efficient implementation of Leiden directly by using the NetworkX API, as long as they have an environment that supports dispatching and nx-cugraph. So now, like I mentioned earlier, thanks to the magic of dispatching, this makes the lives of both users and developers much, much easier, because it saved us from having to rewrite all the docs and tests and all of that for Leiden. We were able to add this to NetworkX fairly quickly. And this means that there's zero code change for a NetworkX user perspective. And it also leaves the door open for NetworkX users to actually just go back to using it on CPU for small graphs when this gets added to NetworkX. Yeah, it's really nice that we have to write only one set of doc strings, examples, and tests. And this can be shared between the upstream library and the backend. All the testing and example can be shared. So here is just the official documentation on NetworkX that shows Leiden is now supported. We actually contributed to the upstream NetworkX library and worked with the community to document this. So there's an admonition right there. It says attention about what it means for Leiden to be a backend-only algorithm. And if you're also curious about the speed, on the right is an example of how you'd call Louvain on the same data, how you'd call Leiden from the same data from earlier. It returns a smaller number of communities, only 28 instead of, I think, over 200 with Louvain. And it ran in around 13 seconds this time, so it is a bit faster than the 20 seconds on Louvain. So with that said, I'd like to encourage you all to go out there and try out community detection in NetworkX with dispatching on your own. Just to recap, if there's anything I'd like for you to take away from this talk, it would be graphs are useful and great for modeling relationships in data. Sometimes relationships are more key than the data points themselves. NetworkX is super user-friendly. It's easy to use for anyone. Dispatching is really great for keeping things simple both for users and developers, and it's also nice that it makes everything super fast. And we love hearing from you all, so if you have any requests for algorithms or features or thoughts about the current state of NetworkX, please reach out, and we'd love to hear your thoughts.
We have about 10 minutes for questions, too, if you're willing to take a couple questions.
Oh, yeah, just one second. Yes, so we have more notebooks that we can, in our showcase, if you want to try it out for yourselves. And I'd also like to mention that we have a Colab example, and NetworkX and nx-cugraph actually come installed by default in Google Colab with a decent-ish GPU, I think. So you can go ahead and get started right away. And please reach out to us. We love hearing from you. Yeah, thank you, and I'll open it up to questions. Yes?
If you find yourself sometimes deploying on environments that may or may not have a GPU, will rapids degrade to CPU?
Yes, the default mechanism is that if there's no GPU in the environment that supports dispatching, it will fall back to the CPU-only implementation if it exists.
But I guess my question is, can rapids run on a CPU instead of, because there's CPU of Python and then there's CPU, like the CPU version of rapids should still be much better.
Rapids is, I can't say for all the rapids libraries, but for graph, it's mainly for running the compute on the GPU itself. There are other backends that actually make use of different ways to speed up code on the CPU, and you can actually specify a list of backends in order that you want your environment to try them in. So if the GPU isn't supported, it'll fall back to another faster NetworkX backend before falling back to default CPU pure Python NetworkX. Does that answer your question?
I get it, yeah, but just in general, you can't run rapids on a CPU.
No, rapids is.
You can't run QML. There's a CPU backend.
Oh, QML runs on CPU?
Well, you can at least run. You can't actually run the code, but you can compile it and run the workflows.
Yeah, I'm not.
It's not all of rapids.
Oh, yeah, it's not all of rapids. Some libraries may support that. Yes?
Yeah, great talk. Can you talk a little bit about how the actual GPU affects performance as far as quality of the GPU? You said you need a decent GPU. How big of a difference is it having like a 3080 versus like a H100?
I'm not too sure on the exact, like, this is this many times better than this, but we have seen significant speed ups when we do like a lot of benchmarking on GPUs that are maybe 5 years old or 6 years old that aren't designed for like large scale AI data center workflows. Obviously, H100 is going to blow a 3090 out of the waters, but we have actually benchmarks in our docs that show the different algorithms, and that should also give you a good idea of the speed you should expect on a specific system. Yes?
Do you support graphs for LLM and RAG databases? Or do you have support for that?
In the backend NetworkX space, we're still exploring like end-to-end workflows using GraphRag. I'm not too sure what other Rapids libraries have been doing, but that is an effort that we're looking into right now. Yes?
When you call like make a backend call like the community detection using Rapids, I assume there's always a one-time cost to translate into like a tabular format that runs in the GPU.
Yes, there's having the data on host memory like CPU versus GPU memory. So if you actually started with the graph on CPU, decided that it's too slow, and then want to go to GPU, there is a one-time conversion that tends to make the algorithm run a bit slower. But once it's on the GPU after the first run, it's actually cached. So the next time you call it, it's way faster. And the way to get around that is to just start using GPU so that when you create the graph from your data, it exists on the GPU first rather than only on the CPU.
Like cuDF? cuDF. So you read
Oh,
the
yes,
data
yes.
first.
So the integration with NetworkX is not just compute, it's also like storage.
Yes, there's a new graph type where it's like GPU graph versus CPU graph, or a compatible graph that might exist on both. Yes?
With one of the algorithms, it might have been Lynan, you showed that the graph creation and the algorithm were both like 20 seconds and 5 seconds. Where did the other 2.5 minutes come in?
The 2.5 minutes, I'm not exactly sure where the time difference comes from. That was from just timing the actual script that I showed on screen, from just running it at the command line. And then the creating a graph and running the community detection was just timing the call itself within the same environment. It wasn't done in this script. Yes, back there.
Are you constrained to dispatch like a non-node-centric algorithm as well? Like algorithm that computes topological signals, like triad and syntheses and things like that?
Are you asking if we plan to support a specific category of graph algorithms?
Non-node-centric, for syntheses and topological features like topological spinners and things like that?
I'm not too sure. So we do have efforts to support different kinds of features in the backend, and we're trying to prioritize them as needed based on what we hear from the community. So if you want to see something supported or want to get a better idea of the current state of the roadmap, please reach out to us. We'd love to hear your thoughts. Yes?
Thanks for the presentation. I don't have too much experience with NetworkX
Mhm.
graphs in general, but I was wondering if the nx-cugraph supports like data visualization and like kind of, if you're creating a data set and exploring it for the first time, like look at it visually, like if there's going to be much GPU support for the visualization.
Yeah, that's a great question. We're actually currently in the effort of trying to take the graph on GPU and also see if we can accelerate the visualization part of it. And as of now, the current state of visualizing still has a lot to do with things like OpenGL and WebGL limitations, and with that comes everything being in JavaScript. So even if it's on GPU, there's a lot of steps that have to run on CPU first before it gets visualized. But to summarize, we're still looking into better visualization support by looking at in-house solutions that we can come up with instead of having to use existing ones. I've had decent experience with using things like Sigma.js to visualize almost 1 million node graphs, maybe 500,000, which is still pretty fast and pretty big.
We have time for maybe 1 or 2 more questions if we have them.
Yes?
So you mentioned that there was a little bit of overhead for actually getting the graph into the GPU. At what scale does this actually perform slower than the native Python? Or like, are there any places where this isn't a pure improvement? It seems awesome.
Yes. Good question. On the really small graphs, NetworkX just does a good job. Since it's a small graph, it doesn't have to do that many operations. And then the GPU tends to lag behind because most of the time is spent doing the actual copy over.
Can you like give a sort of range of like what size of graph you would expect this to not actually be faster on?
Yeah, actually, in this example here, we have a lot of benchmarks around that 1 minute 50 second-ish mark. So around that size of graph is where GPU tends to be a little bit slower, if not eclipsing NetworkX, but NetworkX still performs comparably.
Gotcha. So if we only have like a couple thousand rows, probably not a huge improvement.
Yeah. I have noticed that some algorithms on NetworkX will run out of memory just from doing an algorithm compute thing, but the GPU will not, even if NetworkX would be faster. Is that all the questions? Okay. Thank you very much. I hope to connect with you all.